Hi, it's Mr. Anderson, and this is Environmental Science Video 3. It's on geology, which is the study of rocks and how they change over time. And in this class, more appropriately, how that affects human society. Now, the problem with rocks is that they change slowly. They change over geologic time, and we simply don't live long enough to see all these changes occur. You could imagine how this sandstone is being shaped by the wind, but you can't see it. And it's not until we see lava that we really start to understand the dynamic Earth. And to understand these systems on the Earth, we should really understand how the Earth is put together. And so if we look at the layers, on the inside we have the inner and outer core, we then have the mantle, and finally we have the crust. Now we live on the crust, and we've only been able to dig just a little bit into the crust. And so we've been able to figure out everything else by looking at how earthquake waves move through the Earth. And we know this, that the crust is made up of rocks and minerals. Rocks are made of minerals, which in turn are made of molecules and atoms. And they're constantly being reshaped, and we can measure that through the rock cycle. Now the crust itself is made up of these large continental and oceanic plates, and they float on the mantle itself. And so this is rock under here, but it's rock that's moving. As we generate heat, as it moves up, it's pushing those plates around. They move very slowly, about the same rate that your fingernails grow, but they have huge force and therefore huge impacts. And so when those plates run into each other, we have boundaries. An example of that would be the Ring of Fire. So if you look around the Pacific Ocean, you have this area where almost all the earthquakes and volcanoes take place. We also have what are called hotspots, and those are going to be areas where a plate will move over a hot area in the mantle, and we can form islands like Hawaii. Now, if we look at where those boundaries occur, we'll have structures like volcanoes and mountain chains, but we also therefore have hazards around those areas where it can impact human society, and we'll discuss a lot of those. And so to understand what's going on the Earth, we should really understand what it looks like on the inside. So we've got a solid inner core, a liquid outer core, and then we have what's called the mantle. Now, around 85% of the volume of the Earth is going to be in this mantle. And so it's rock, but it's rock that's moving. We're generating a huge amount of heat down here. And then we finally get up to what's called the crust. That's where we live. And so on that crust, we have rocks. And those rocks are constantly being shaped from one into another. And so if we take a look at this rock cycle, since it's a cycle, you could start anywhere. Let's start with an igneous rock. So an igneous rock, like granite, is going to be formed when we have crystallization of magma. So as it crystallizes, you can see those crystals right here. So this granite is made up of minerals. So I can see, for example, this quartz and this pink feldspar, and we have this mica. So these are the minerals that make up the rock itself. But this could experience erosion. So erosion on the planet, water, wind, can cause it to break down into sediments. And therefore, after it's done that, it could get squeezed for a long period of time, and we could have a sedimentary rock, which is going to be compressed sediments. Now that could be squeezed. We could squeeze it under the surface of the Earth using heat and pressure. It could form something like quartzite. Or we could take that igneous and we could squeeze it and make something like gneiss. And so GNEISS, it's a type of metamorphic rock that's formed by the squeezing of granite. Now you can see those minerals are still there, but it has a different shape. And so the rocks on our planet are continually recycled over and over and over again. But if we get back to the structure of the Earth, what's driving all of this are going to be convection currents within the mantle itself. And so if you look at this and say this is some boiling water, so if we generate a little bit of heat underneath it, that heat is going to be transferred through the water. So if you held your hand up here, you'd feel some of that heat above it. But if we look inside the water itself, we're going to have these convection currents, areas where we're heating it up, and so we're decreasing the density, and then it cools down, and then it's going to sink again. And so we're going to find the same thing in the mantle itself. It doesn't occur as quickly as it does in the boiling water, but it has huge implications on the crust above. And so if we look at that crust, it's actually made up of plates. And so if I trace out a plate like this, this would be a continental plate. And so it's being pushed to the left. And the reason why it's being pushed is because of this convection current is moving like that. It's forcing the plate in that direction. And it's running into another plate. So we have an oceanic plate. The oceanic plates are going to be more dense, and they'll be pushed underneath a continental plate. And what we're going to get right along this margin is going to be a convergent plate boundary. They're running into each other. But we could look over here, and maybe there's another oceanic plate that's moving in the other direction. Why is it moving in the the other direction because the convection current is pushing it here or pushing it there. And so we could have this mid-Atlantic ridge or this mid-oceanic ridge being formed right there. So we've known this for a long time. If you look at the Ring of Fire, we find around the Pacific Ocean we have an aggregation of volcanoes and earthquakes. Something like 75% of all volcanoes, 90% of earthquakes are found in this area. If we start plotting where those earthquakes are, we can start to see where those plates exist. And if we look at the plates on our planet, it's hard to wrap your head around this picture for a second. So this is North America right here, and then it sits on this giant North American plate, and then we'd have the Pacific plate right here. And so those plates are constantly moving around. You're probably familiar with Pangea, which was a time when all the continental plates had come together. So what happens when plates meet is that they can do one of three things. They can slide past one another in this transform boundary. They can move apart. We call that a diverging boundary, or they could run into each other. That's converging. And so if we look at an example of that, right here we have a convergent plate boundary. So what's going on? We've got this oceanic plate which is being pushed or subducted underneath the continental plate. I described that just a second ago. What's happening is we're melting that rock, and that's forming this volcano chain that goes all the way back here. Example could be the Cascades in Washington State. We could also have a convergent boundary right here where we have an oceanic plate going underneath another oceanic plate. And we get this island arc like the Aleutian Islands in Alaska. We could have divergent boundaries. An example could be right here. So we have this oceanic plate moving away from this oceanic plate. So we get this mid-oceanic ridge. We could have a rift valley where this continental plate is being pulled apart. We could have transform boundaries. Here would be an example where they're sliding past one another. San Andreas Fault is a good example of that. But we can also have structures where there is no boundary. So if we look right here, we have what's called a hot spot. Remember, that's going to be an area where the mantle is close to the surface. And so, for example, Hawaii was formed as the plate slid over a hot spot. And let me show you what that looks like. So if we imagine that's the hot spot, it's going to be underneath the plate. And what's happened to Hawaii over time is it slowly slid over the hotspot. Hotspot stays in the same location. And so we've had volcano after volcano after volcano. And so this is the most recent volcano, and we'll have another island right here. And the reason there's smaller islands out here is that there's more erosion. Yellowstone National Park is another example of a hotspot and the plate simply sliding over the surface. Now we get to humans and human society and how we start to interact with the structures of the Earth. And so living around these boundaries can be dangerous. It's just a matter of time. So an example could be volcanoes. Some volcanoes, like the ones we would find in Hawaii, can ooze out. And as long as we're able to move out of there quickly, we're going to be fine. But some are highly explosive, and it depends on what minerals make up that rock that determines the explosiveness of the volcano. A very explosive one I remember is Mount St. Helens. And so this is a picture of Mount St. Helens in Washington. This is the day before it exploded. And so just take a second to imagine that's the structure of the volcano, and now it's gone and rebuilding again. And so it literally blew apart. And if you were on or near that, you died. Earthquakes are another example of a natural hazard. What we have are faults, and this would be a fault right here, and we have one plate, in this case transform fault, where it's sliding past one. We could also have a divergent boundary, so these two are moving away from each other, and so we have what's called a normal fault, it's slipping down. Or we could have a reverse or thrust fault when we have a convergent between these two areas on either side of the fault. Now the names are not as important in really understanding what's going on in an earthquake. If you think about it, if we have two plates that are pushing on each other, eventually they're going to build up pressure and it's going to slip. And as it does that, we have an earthquake. So if we watch this right here, let's say there's pressure in this direction, and eventually it builds up and we have a slide along that fault line. Now it's not like it's stopped, there's still pressure there. We could have another earthquake in the future and another earthquake in the future. As these move past each other, it's just going to move in small slips. And every time we do, we have an earthquake. Now, if you're standing on the surface and there's an earthquake, you're going to be fine. The problem is if we build structures on that and it's not earthquake ready, then those fall in and humans are going to be impacted. We could also look at tsunamis, which are caused by earthquakes. What we've got here is a subducting oceanic plate. This would be a continental plate. And what's happening is this is being pushed underneath, but it'll just stick. And so it's not going to release, and as it sticks, then we build up pressure, and then eventually when it slips, what we get is a huge push up on the water above it. So you get this vertical motion in the ocean, and that leads to these giant tidal waves. And so if you're near the ocean, you would also suddenly notice that the ocean's going way out, and then it's going to come way in, and there are really bad consequences from that. We could also have mass wasting, so an example could be a landslide moving across this road. This is a picture taken before, and then watch it after a landslide. Now, it doesn't occur really quickly, could be triggered by an earthquake, but generally if we get a lot of water in an area, it can't support that weight. And so did you learn about Earth systems? Can you stop the video and try to fill in the blanks right now? I'd pause the video, but if not, I would say we've got a center core, we've got a mantle and a crust. The crust is made up of rocks, which in turn are made up of minerals, which is reshaped using the rock cycle. These plates move on the surface. We call that plate tectonics. An example would be the Ring of Fire. Where we have boundaries, we can build up structures like volcanoes, mid-oceanic ridges, but we can also have natural hazards. And then remember, not along boundaries, but just within the plate, we can have hotspots. So I hope you learned all of that, and I hope that was helpful.